So it's a very great pleasure to introduce the second speaker of today, Professor Vardan Papyan from the University of Toronto. I first learned about Vardan's work through his paper with Donahoe and Han on neural collapse. And today he's going to talk about the emergence of block coupling and its correlation with generalization.
Hello everyone, thank you very much for the invitation. The work I'll present today has been done jointly with Murdoch Aubrey, Jianying Li, Haoming Men, and Anton Sugalov. And it will be based on the following couple of papers. One was presented at NeurIPS, another one is going to be presented at the upcoming ICLR. So as we all know, there exist several fundamental components in all modern deep learning architectures. These include affine transformations, activation functions, normalization layers, attention, and most importantly for today's talk, skip connections. So skip connections were first introduced in 2015 in the seminal ResNet paper, in the form of the ResNet block on the left, and they have since been adopted in pretty much every single deep learning architecture that's used today, including the transformer architecture that is essentially the basis for all modern large language models. And just to give you a sense of how important the skip connection has been, here's a quote from the Wikipedia page on Kaming He, who was the lead author on the paper that essentially invented the skip connection. And the quote says, his 2016 paper, Deep Residual Learning for Image Recognition, is the most cited research paper in all of science for 5 years, according to Google Scholar reports. Across all of science, 5 years. Just something to keep in mind. And so the question is, why are skip connections so useful? And so the prevailing explanations that researchers usually provide is that they facilitate gradient flow, which means that you're able to backpropagate the loss better to earlier layers, that they improve the training efficiency, they allow you to train deeper architectures, and so forth. The point of this talk is to say that skip connections are actually doing much more than just that. In order to explain why, I need to introduce certain definitions. So first of all, we're going to denote by xi the representation coming out of the ith layer. This is very hard to do. Okay. Xi is the representation coming out of the ith layer, and that representation is being fed to some kind of a block, either a ResNet block or a transformer block, and that block has a skip connection, which is this thing, right? And so the block is calculating fi xi, which is usually called the residual, and the residual is being added to xi to produce the next layer's representation. Now, what we're going to do is we're going to take these blocks, which are essentially nonlinear blocks, and we're going to linearize them through Jacobian matrices. So we're essentially going to differentiate fix with respect to its input, and we're going to evaluate it at a point xi. So assuming that the representations are d-dimensional, this Jacobian is going to be a d by d matrix. And then what we're going to do is we're going to take these Jacobians and we're going to calculate their singular value decomposition. And then we're going to do something a little bit strange. We're going to take this singular value decomposition and we're going to create what I call a sandwich. This is a sandwich. This sandwich takes the Jacobian of the ith layer and it hits it on the left and on the right by the singular vectors of the jth layer. So we're taking the Jacobian of the ith layer, and we're trying to hit it on the left and on the right with the singular vectors of a different layer. Now you might say this is a little bit strange. What we're going to do is we're going to inspect these matrices, and we're going to check if these matrices are roughly diagonal. If the matrices are roughly diagonal, we're going to say that the I and J layer are coupled. So at this point, I would like to stop for a moment and ask if these definitions make sense. If they do not make sense, the remainder of the talk is a waste of your time. You might as well ask something now. If you don't want to waste your time, that is, which probably is the case. Yeah. Any questions? Yeah.
Do you not think that each layer has the same number of dimensions? Has the same dimension?
Right. So this only makes sense if the layers have the same dimension. Otherwise, this is just impossible to do. Right? Yeah. 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 Lucky for us, any modern large language model has the same embedding for all the transformer blocks. If you look at the input-output, right? If you go into the block, maybe it changes. So you could do that. Lucky for us, many architectures have the same dimension for a sequence of layers. So you could look at those. Yeah. In linear algebra, how do we call the phenomenon where a certain matrix can be diagonalized by the eigenvectors, for example, of a different matrix? How do we call that? Anyone knows? Yeah, exactly. Co-diagonalizable, simultaneously diagonalizable is how you would call it. Okay, yeah.
So the number of layers, does the number of layers in one model affect the result here?
So far, there's no result, but the number of layers would affect, basically I and J have to span over different layers, right? So I and J are between 1 and the number of layers.
So if I have 2 layers, then it's already like effective to apply the result here, like apply any result you will present next.
I didn't. Sorry. Yeah.
Like, so if my model had 2 layers, and if my model had 10 layers and 100 layers,
yeah.
What's the difference in the result?
So far, there's no result, but you would. The more layers you have, the more things you can compare, right? So I, J are 2 layers in the model. If you had 100 layers, you could pick 2 layers from those hundreds, right? Does that make sense?
Yes.
Yeah.
So I guess these are Jacobian maps, right? Not just matrices, so you evaluate them at every point. So
yeah.
So to relate to different layers, do you make sure that they are evaluated at the point that makes sense? I would assume
no, we don't actually. That's a great point. Okay, just let us digest what you said. So first, just a moment. So are you asking if we take 2 Jacobians, right, and the 2 Jacobians correspond to the same input?
That's what I would assume.
Oh yeah, they do correspond to the same input, yes. But, yes, okay, yeah. I thought you asked something different. Because you could ask something a little bit different, which is you could ask, do we evaluate the Jacobian sort of like at the same representational input or something like that, right? Okay, yeah. So we do something that makes sense. Mm-hmm. Okay, so hopefully.
One last question.
Yeah.
Does the difference between I and J matter, and can be?
It will matter. Yeah.
Okay. Is J always larger than I?
No. But I can see why you might ask that. Yeah. Okay. Actually, it's important if J is greater than I or less than I. It's very important, empirically. Not very important, but I would say of importance. Okay, so now that we understand this definition, what we're going to do is we're going to take a certain ResNet architecture that was trained on the CIFAR 100 dataset, and we're going to look at a grid of plots. Each little box here, let's say this box, is plotting this matrix right here that hopefully we understand what that is. It's plotting a sandwich, okay? The one thing is that we're only taking the top k eigenvectors for some k. And what do you see, right? You see that here is, for example, the ith layer, and here is the jth layer, right? So each one of these is showing the interaction between 2 layers. And what you can see is that in many cases, the matrices look roughly diagonal, right? Roughly diagonal. Why do I use the word roughly? Because this is empirical. Life is imperfect, right? You don't get diagonals. You only get diagonals in math, not in life. Right? Okay, one thing I would like to emphasize is that one of the people here asked about layers having different dimensions. So here we're looking at the interaction between layers before the pooling, because those have the same dimension. And here we're looking at the interaction between pairs of layers after the pooling, because those have also the same dimension. One thing you can notice here is that deeper layers have stronger coupling than shallower layers, right? Because here maybe the coupling is somewhat weaker. And you can also see that for layers that are closer to each other, which means that they're closer to the diagonal, you are able to couple better. And one last comment is, notice that on the diagonal, the coupling is in fact perfect. Why is it perfect? Yes, by definition, essentially. Because this, yeah?
Yeah. Just a question. So how much do these plots depend on the input that you feed into the network?
Generally speaking, this is what you see. How much does it depend on the input? What do you expect the dependence to be, if you had to guess? I'm trying to probe what is your hypothesis.
I don't have one. Yeah.
Oh, okay.
It might concentrate and look like this a lot.
Yes, that's our impression. One thing that I'm hypothesizing but have no evidence for is that maybe the coupling occurs. So for example, in certain cases, the coupling might occur very early. In certain cases, it might occur later. In certain cases, you might be more coupled overall than others. I think those are important questions, and they might relate, for example, to the difficulty of the input, which is undefined mathematically, of course. I'm unable to answer your question, I think. Okay, so this was done for a ResNet architecture. The next thing we do is you could claim that this result was done by us, and we train our architectures. Maybe we don't know how to train architectures and so forth, right? So what we did was we took an architecture trained by competent individuals. Who are they? Meta. Have you heard of Meta? It's a good company. So Meta released a model called Llama 3 8 billion. It's a very big model trained by them, not us. And then we feed to that model the prompt, which is, what is the capital of France? The capital is, and then you need to predict what is the capital of France, right? And so as you predict the next token, which is the word Paris, right? You get a sequence of embeddings through the model, a sequence of embedding through the model, and they again define these Jacobians that you could try to check if they're actually coupled or not. Does that make sense? Basically, you repeat the same measurement for Llama 3. And what do you see? You see that, similar to the previous slide, there seem to be a lot of diagonals, a lot of diagonals, a lot of diagonals across the board. In shallower layers, you can see that maybe you need to really zoom in to see the diagonals, but they are there. They are there. A lot of diagonals. A lot of diagonals. A lot of diagonals. Okay, so at this point, you might be asking, what is causing all of this coupling between the layers? So we decided to do an intervention. So we trained two models. One is the usual ResNet that has skip connections, and another model where the skip connections were removed. Once you remove the skip connections, you can see that now there is absolutely no coupling, bless you, except on the diagonal, except on the diagonal. And so that means that if you remove the skip connections, there is no coupling. Okay. Now, another thing you might ask yourself is, what is the role of training on this coupling metric? So what we did was, we took these measurements right here, and we took every pair of layers, right, I and J, and we distilled the coupling into a scalar that's essentially measuring how diagonal are we, how coupled are we. And then you can actually track this metric as function of training. So here we're looking at the Pythia model. It's another model that was bestowed upon us by a company that has a lot of resources. Pythia, 12 billion parameters. And we're looking at various checkpoints throughout training. So it's throughout the training of the large language model. And then here, each one of these boxes corresponds to a different transformer block, 1, 2, 3, all the way to 29, which is the deepest one. And you can see that there's edges that are being connected between pairs of layers. Those edges encode how coupled are those two layers, right? And so the point is to investigate how does the coupling between the layers emerge as function of the training of the large language model. Do these words make any sense? They do. And one thing you can see is that roughly around checkpoint 2000, something starts coupling at the very top. Don't blink, don't blink. Oh, here you see, at the very top. And you can initially see that the coupling emerges locally because you sort of see the coupling on the outer ring, but then as you continue training, it sort of like becomes coupled even between far away layers, and the whole graph becomes dense. See it again, you see? Becoming denser and denser and denser. Okay. And you could actually take all of these coupling metrics and reduce it further to a single number that tells you how coupled is the model. And so here we plot this coupling number versus the checkpoint of training. And what you can see is that the coupling is, roughly speaking, monotonically increasing as function of training. The more you train, the more coupled the model becomes. And one thing to note is that this checkpoint is actually it's on log scale. So the further you couple the system, the harder it becomes to couple it even further. Okay, at this point you might say to yourself, okay, maybe you're convinced that there's some form of coupling, but maybe it's irrelevant, right? Maybe no, it's just some strange thing that happens in the model and it is of no significance. In order to check what is the significance of coupling, we decided to test whether coupling is related to the performance of various large language models on downstream tasks. So people take these LLMs and they test, can they solve our math problems, right? Can they help us solve high school problems? Can they help us do research? There's various benchmarks out there that essentially assign a score to these LLMs. And so here you can see, for example, GPT-2 is a very old LLM. You can see Pythia that I mentioned earlier. And you can see that there's Llama 2 all the way to Llama 3 and so forth, right? And so what I'm trying to tell you here is that if you try to correlate coupling with the downstream performance, there seems to be quite a trend here with a statistically significant p-value. And so it seems like coupling is correlated with generalization. Some reviewers kept telling us that maybe there's various confounding factors here, like maybe the scale of the model, maybe the number of layers, maybe I don't know what. And so we did a bunch of experiments where we tried to check if there is anything that correlates better with the downstream performance. And we actually couldn't find anything that correlated as well as this. One thing that is of interest is how can you actually make coupling stronger or weaker, right, besides just training for longer. And it turns out that there is a technique in the literature that actually amplifies coupling. And the technique is called stochastic depth. Stochastic depth is a roughly well-known technique that essentially says during training, I'm going to skip a certain block with a certain probability, right? And people have noticed that that leads to better generalization and is generally useful. So we decided to test what happens if you use stochastic depth or if you don't use stochastic depth. How does that affect the coupling? And so here's the coupling measurement for a model trained without stochastic depth, right? And you can see a bunch of diagonals all around. But then, if you suddenly use stochastic depth, you can see that the coupling is actually much better. So if you look at the bottom left and the top right, you can see that with stochastic depth, there is more coupling. And so it seems like regularization techniques are actually able to amplify coupling. Now you might ask yourself, what is this coupled subspace, right? All of these Jacobians are coupled in some sense, and so there's some kind of a common subspace that they share. What is that? So in order to try to investigate that, we decided to test what does the dimension of the coupled subspace depend on. So we trained a bunch of architectures on CFAR 100 once it was subsetted to various numbers of classes. And what you can see is that if you have a small number of classes, then the dimension of the coupled subspace is the number of classes minus 1. And so here it's 3, here it's 5, and then it increases the more classes you have. So it seems like the low dimensional subspace of these coupled Jacobians is somehow related to the labels. So one thing that's interesting about coupling is that coupling actually induces what I call representational trajectories. So here what we're doing is we're fitting the same prompt I showed earlier, what is the capital of France, the capital is, throughout the layers of a llama model, and then we visualize using PCA the representations as they evolve. And so each one of these colors corresponds to a different tokens, and the animation sort of shows how the tokens evolve through the layers of the model. And what you can see is that all of these representations, they essentially move in a manner that sort of, it looks like some kind of a very smooth trajectory, at times almost linear trajectory, extremely well-behaved, I would say, extremely well-behaved.
So where is coupling in this picture?
Coupling is, okay, the fact that you're even seeing anything, I would claim is coupling. So if you think about it, imagine you had like a bunch of representations in a model, and they were not related to one another, right, in any shape or form. If there is no coupling between the layers, you would just see garbage, right, if you did PCA. Another way to answer your question is that coupling essentially implies that the trajectories of representations could be modeled almost like through ODEs, right? And so essentially you could think of these trajectories as being sort of like ODE type trajectories. That's one way to think about it. I don't know if this answers your question.
So just following up
Yeah.
on that, you said that you're projecting using PCA.
Yeah.
So the point is just that you're choosing the
Principal
PCA directions
components.
in each of the layers separately.
If you were to do it for each of the layers, it wouldn't work due to reasons that are complicated to explain. Because you would keep jumping from like one basis to another. So it's actually some kind of like a global PCA across everything.
Right. So yeah, so I'm trying to get at that. So I mean, it seems to me that what you're trying to show using coupling is that there's some privileged basis for your
Yes.
single
Yes.
vector space.
Yes, that is.
that-
Are you
that
affiliated
everything-
with a certain large company by any chance? No, never mind. That's the. No, there's a company, Anthropic. They use that terminology.
Yeah. I mean, what this is suggesting to me is that these privileged basis directions should be associated to concepts in some way.
Right,
or
right,
features.
right.
You know,
Yeah.
so,
Yeah.
But I'm just trying to get at, for these plots,
Mm-hmm.
what are these plots of?
Oh, in this specific case, we're showing the evolution of a certain token throughout depth. And
But-
so,
But when you compute each plot in this movie,
yeah,
what are you, which basis you're using?
PCA, so it's basically just trying to find a basis that maximizes the amount of information once you project to it.
So like a single PCA or a different PCA?
Oh, it's 3 principal components. That's why you have X, Y, Z. It's a single PCA across everything, so you have only 3 vectors overall. It's definitely related to, I have a lot to say on the privileged basis. I think we could talk about it at length offline. Okay, so another thing you could do is you could actually take all the representations of all the layers across the whole data set, let's say CFAR10, and you could just project them to 2 principal components. And if you do that, you see something very interesting. So here, each one of these trajectories represents sort of like the evolution of an image throughout the depth of the model. And so an image starts around the origin, where you have like something that looks like chaos, and then an image is being pushed by each layer in a certain direction. And each one of these dots corresponds to a different layer. So this is the input, and then you go to a deeper layer, deeper layer, deeper layer, deeper layer, and so forth. Now, the reason we have so many different trajectories, right, is because we have so many different inputs, right, so many different images in the data set. And each one of these colors is encoding a different class, right? And what you can see that maybe you did not initially expect is that all of the images in a certain class are being pushed in a very predictable manner, sort of in a trajectory that looks almost linear, right, in a certain direction. And so you're essentially taking all the initial images, right, and what you're doing is you're sort of like, this is the animation in my mind, right? You're taking all the images and you're sort of like pushing them, all the images in a certain class, in a certain direction, right? And that's the way the model is able to separate these classes.
So
Yes?
then what does this have to do with the coupling?
Okay, what does this have to do with the coupling? Imagine if you have a set of layers that are literally coupled. If the layers are literally coupled, right, what you would expect to see is a trajectory that's essentially behaving like the trajectory of some kind of like a, almost like a differential equation, right? Actually, I can see why it's not trivial what I'm saying, but that's sort of like a consequence. So, okay, maybe to answer your question very directly, you're asking how is this related to the coupling? Notice that if you start at this layer and you go to the next one, right, the residual is basically this much. And then in the next layer, the residual is this much. And the next layer is this much, right? Notice that the vectors are basically the same. Each layer is basically shoving you in the same direction by the same amount, right? And so why is that the case? Because they're all coupled. They're all basically doing the same thing. Does that answer the question?
Yeah, I think so.
You could think of this as almost like a... actually, no. Yeah.
Yeah, I had this question because like the coupling happens on the the diagonal block level, but then this is like a PC over.
The representations, yeah. Yes, yes, yes. The thing is, like, if all the blocks couple, right, then you can write the equations and you would see that the whole network becomes almost like a differential equation. And then if you take a differential equation and you initialize it with an eigenvector of the coupled matrix, you would essentially be moving in a linear trajectory. I think that's what's basically happening here. Hmm?
So are the principal components like close to some of the privileged basis vectors?
In this specific case, the principal components are some kind of a linear combination of the different classes. And the reason you can see that is because the principal components capture the class information, right? And so in this case, you have 10 classes, but only 2 principal components. And so what happens is that you just project onto some kind of a linear combination of these classes. Does this answer the question?
Yes, yeah.
Mm-hmm. So this, everything I'm presenting here, oh, a question, yeah?
Back to the previous
Yeah.
picture. If we consider just all the layers are coupled, in this case, does this mean that the the classification performance of the ResNet is based on the first layer?
Yeah, that's a beautiful question. I have an adversarial graduate student who keeps saying that. Adversarial in the most positive manner, I must say. This is a very interesting question. I'm still unsure about that. I'm still wondering the same question. Generally speaking, in deep learning, people think that depth is beneficial for accuracy. Many people do linear probes, where they sort of like probe the accuracy as function of depth. And generally speaking, the accuracy goes up, right? But the thing is that that seems to be against, right, the fact that you're coupled. We're still investigating how to align those two things. One hypothetical answer is that maybe for certain inputs you couple very early, and for other inputs you couple much later. And so you're saying like a bunch of layers might be useless. Maybe they are useless, but the thing is they're useless for one input but not the other, right? But I'm not sure, I don't know. What do you think? You think there are a bunch of useless layers?
I think your guess is
Reasonable,
reasonable.
okay. Because if you say it's a bunch of useless layers, here's one thing I could say. If there are a bunch of useless layers, if you look at Llama, right, that's trained by a competent company, right? Meta has a lot of people who know how to train models, and they're showing like a lot of coupling, and the coupling intensifies with scale. Like, how do you explain that, right? Strange. And in in the Llama case, actually, something is bizarre, because the coupling actually is happening in the middle of the model. It's not actually at the very late stages. And so because of the location is in the middle, it means that you cannot, yeah, I'm not sure. It's a very interesting question. I think that's one of the most interesting questions. I'm just not sure. Okay, so this whole, everything I've spoken about is actually related to some extent to neural collapse. So neural collapse, as mentioned in the beginning, is a paper we did with XY Han and David Ono in 2020. And what that paper is showing is essentially that if you look at the representations of the penultimate layer of classification models, then the representations in a certain given class as function of training collapse all to a point. So essentially all the representations of a certain class become equal. And not only do all the representations of a certain class become equal, all of the different classes have certain class averages which form this perfect geometric structure, which we call the simplex ETF. And also the classifiers of the model, which are essentially these vectors, align with that perfect geometric structure. And so one of the motivations for this whole investigation that I've shown you is to try to understand not only what is happening at the very last layer, but actually what is happening through all the layers. And I think that's related to the talk we'll see afterwards, to some extent. And so one thing that people were interested in recent years is actually trying to extend neural collapse to earlier layers, to try to understand what is happening in all the layers, right? How do you eventually get to neural collapse? And so people came up with this idea of deep neural collapse, which is the idea that gradually the layers are somehow managing to collapse all the representations in a given class to this perfect geometric structure. And here you can see a list of works that studied this deep neural collapse phenomenon. I think that what I'm presenting to you to some extent explains why you have neural collapse, why you have deep neural collapse. What you can see is that all the layers of the model are taking the initial input data and are essentially gradually pushing it towards the direction of this simplex ETF structure. You can see that gradually all the representations are being pushed in a certain direction by all the layers. And so I think to some extent this explains why people observe things like deep neural collapse, gradual collapse as function of depth. How much time do I have left?
It'd be great if you could finish in like 10 minutes or something.
10 minutes, okay. So I think one thing that people have actually observed is that you can measure some form of linear separability as function, or some form of neural collapse as function of the depth of the model. And if you do that, you actually see that there's this beautiful power law that emerges. So essentially what's being plotted here on the y-axis is how collapsed are the different classes, right? In the first layer, or in the 0th layer, you can see that the classes are all intertwined, non-collapsed, and so forth. But the deeper in the model you go, the more collapsed these classes become, right? And so you can actually quantify how collapsed the classes are through some kind of a metric, and you can track that as function of depth. And you see that there's this beautiful power law that emerges, right? The question is, why is this power law emerging? Why do you see that the rate at which the model is collapsing the different classes is so predictable? So again, my answer to that is this figure, right? This figure is showing that all the layers are gradually pushing all the images in a certain class in a certain direction, and because it's all done in such a beautiful manner, right, such a structured manner, you get phenomena like power law, right? That is why you see that, right? The rate is very predicted by a power law just because all the layers are just gradually pushing the classes towards the simplest vectors. Okay, so at this point, what we wanted to do was try to explain mathematically some of the phenomena that we've observed. And so inspired by theoretical works on neural collapse, we proposed what's called the Unconstrained Jacobians model. So this is a theoretical model for studying these empirical phenomena. And the idea goes as follows. Imagine that you have a single input in your whole data set. And assume that there's a corresponding binary label, +1 or -1. The goal of our goal, essentially, is to minimize some kind of a loss, right? And the loss depends on your input data point and on the labels. Now, the input data point is being multiplied by a bunch of matrices, right? And you can see here there's the identity, which is what? The skip connection. And you can see the Jacobians, right, which are matrices. And we're assuming that the matrices are not coupled. In fact, what we assume is that the Jacobians are some optimization parameters. Does anyone find this strange? Does anyone want to object?
So it's just linear?
Okay, so one might use the word just linear. Just linear. When you say just linear, I think what you're saying is essentially deep linear model, right? Yes, 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 yes. And so I think it's definitely related to just linear models. I feel like just linear is a little bit too. No, I'm just kidding. It is just linear. But I think that one thing that is very important to note is that classically speaking, as far as I'm aware, when people study just linear models in the theory of deep learning, they literally assume that the model is just linear for all input. But here we're assuming that the model is behaving like a linear model for a given input, which I think is a fundamentally different statement or assumption. So we're assuming the model is just linear at some epsilon ball in the input space around a certain point, right? That is fundamentally different than assuming that the model is globally just linear. Okay, anything else that someone would like to object to maybe?
Why just one input and not sort of have a sum over multiple inputs?
I cannot do anything at that point. It's too complicated. Yeah. Any other objection? Maybe I should object to my own work. Yeah?
How do you control JI?
We control JIs through various regularizations. Yeah. By the way, I should mention that there's also a W, which is the classifier, right? Does anyone want to object further? What's the most objectable thing in this slide? One input is objectable, but you could say like, okay, no one's stopping you from training a model on one input, right? Yeah? Do you want to object?
What is the definition? Like, they know what the definition of what? I don't see.
What is the definition of?
I mean, the object of the definition. Like,
The object.
What?
Oh, the definition is defining the optimization problem.
Oh.
It's a definition of an optimization problem. What is the most objectable thing in this slide? Yeah.
What is the loss?
The loss is cross entropy or MSE, I'm forgetting one of those. But that's not the objection. What's the most objectable thing? The most objectable thing about this slide is that we're optimizing over Jacobians, right? No one's optimizing over Jacobians in deep learning, right? People optimize over weights. They optimize only over weights, over parameters. And so we allow ourselves to optimize over Jacobians for the sake of mathematical tractability, elegance, whatever you want to call it, okay? So that's the most objectable thing on this slide. Assuming you're willing to entertain this optimization problem, then you can actually prove that a global optimum of this problem, which we call the unconstrained Jacobians problem, satisfies the following properties. All the Jacobian matrices are going to be rank 1 matrices. Why rank 1? Huh? So, yeah, why rank 1? One data point, and also the fact that the number of classes is 2, so you get 2 minus 1, which is 1. But yeah, it's also the fact that you have one data point. The second claim is that the top singular vectors of the Jacobians are all aligned, and so that's basically saying that we're able to formalize coupling. The top singular values of the Jacobians are equal, and the intermediate representations lie on a single line. And so effectively, you're able to encapsulate the properties I've presented to you. It's just that it's in this super contrived setting of a single data point, binary classification, and optimization over Jacobians. Quite unsatisfactory, I know. Okay, so to summarize.
Sorry, do all global optima take this form, or just you're just claiming that one of them?
Global. It's possible that you could claim uniqueness. We just didn't even try, just because it feels so contrived that we lack the motivation. Yeah. So to summarize, coupling exists in modern LLMs and ResNets. It emerges with training, correlates with generalization, is amplified by regularization technique like stochastic depth and also weight decay, which I haven't mentioned. The dimension of the coupled subspace is related to the number of classes in simple models. Coupling induces representational trajectories. It explains to some extent the deep neural collapse phenomenon and this law of data separation, which is essentially this power law at which classes separate. And you can theoretically try to understand something through the unconstrained Jacobians model. This is it. Thank you very much.
Thank you so much for this beautiful talk. Any questions?
Any objections? Yeah.
What is the next step?
Sorry?
What is your the next step in your mind?
In my mind.
What do you like to do next?
Yeah, one question that someone, one question is, if the models are coupled, could we actually use that for practical purposes? Another question is, how do you go beyond this very simple theoretical model? I think that a lot of people have spent a lot of time and energy and IQ points on deep linear models, right? And I think that those could all be leveraged to just understanding how does the model behave locally in the input space, right? Because if you take a very complicated nonlinear model and just restrict your attention to its behavior in the vicinity of a certain training point, at that point the whole optimization problem becomes very similar to the one I presented, and all the deep linear model analysis become very relevant, right? Does this answer the question? Do you see any more promising directions you would
I guess
like to propose?
Maybe clarify that it was not totally clear. So another thing that is kind of central is to operate directly at the level of the weights. In the layer, you view it as a matrix of weights.
Yeah.
And then argue about how these matrices kind of align with each other.
Oh, so one thing I should mention is that prior to all of this, we did literally that. I have an obsession, literally an obsession. Some people called me part of a cult, where I truly believed that the weights have to couple. So one thing that I truly believed that the weights should be, like one weight is supposed to be the transpose of another, for example, like if you look at a single block. And we spent an unimaginable amount of time trying to show that empirically, and we failed. We failed. The moment we moved to Jacobians, it was easy peasy, the rest was, smoothness. So the weights, something there is unpleasant and does not couple for some reason. It's also possible we just didn't use the correct metrics.
Okay, any other questions?
I think you just mentioned something like this, but if coupling is important for empirical performance, then could you bake this into the training as like through a penalty term more explicitly?
Yeah. So stochastic depth, which is something people actually use, is one form of doing that. The reason is that the way stochastic depth works is you skip a certain layer with some probability. And so if you skip a certain layer with some probability, in some sense you're forcing things to be coupled, because they have to compensate for previous layers having been dropped. Does that make sense? But that's just one thing that has already been proposed. We're trying to think of ways to do it that are different. Yeah. The extreme case, by the way, of all of this, and maybe that's what people are sort of like pointing to, is if you literally believe that all the layers are coupled, right? If they literally are coupled, you could say that maybe all the weights should be the same, right, in all the layers. But empirically, it's people don't do that, right? People don't couple all the weights of all the layers. So I think there is something subtle here that maybe the Jacobians couple once you look at them locally, but globally all the weights are not coupled across all the layers. Maybe we do need a lot of layers.
Maybe one last question.
Sure, why not? I wanted to ask, so I know that the language models at least, right? As you kind of noted, as training goes, coupling also grows, not with language models, but just in general.
Yeah.
I know with language models at some point, right, we stop training and we don't keep training up until some point. And do you think though, so does that linear correlation or semi-linear correlation between generalization and coupling would keep going, or would it collapse at some point if you just keep training? Or do you think that it's really like sort of like this correlation would go on, or?
The problem is that we don't have the funding to train this LLM, so I can only speculate, right? But one thing I should mention is that we actually, we don't.
Yeah, but sort of a toy example of like outer regression, things like that.
Yeah, I guess we could do that. Yeah, well, but one thing I should mention is that for this specific plot, someone was actually asking us some funny questions. Someone was asking us, why is the 6.9 billion higher in terms of coupling than the 12 billion? And so we actually looked at the, for the specific prompts we looked at the performance of the model, and we actually saw that the performance of the smaller models was actually better. In fact, if you look at the performance for these specific prompts, literally these experiments as function of training, it literally looks the same as this plot. So to me, it seems like they're extremely correlated. But I don't know if there's like a breaking point where suddenly coupling becomes I don't know. It's a great question, yeah.
Okay, so let's thank Vardan again.